Hi guys, welcome to your first video for Survey of Data. I'm your instructor, Haley Dorman, and on this first one I just kind of wanted to do a little bit of intro so you guys kind of know what you're in for with these lecture videos coming up here. So I use my iPad to write down some notes for you guys, and if there's ever something I've uploaded to kind of help us get through the notes a little bit quicker, I'll always provide that to you. But today I'm just basically using like a whiteboard on my iPad to take some notes with you guys and go through some examples for section 1.1 in your textbook. So if you just grab a pen and some paper, you'll be able to go through these notes with me and take notes yourself, which will be useful for completing the homework, studying for upcoming exams and things like that. Okay, so hopefully this is helpful for you guys, and always email me if you have questions or anything like that. The first thing I'm going to do is just stop my video so the whole time you can see the iPad and go ahead and switch over to that. All right, so today we're looking at section 1.1, which is kind of a mixed box of things that we're going to start off with some review. Okay, so we're going to review what variables are, what constants are, inequalities, and how to plot points. Okay, so just a big review of some different topics today that we'll see throughout this class. All right, so the first thing here that we want to talk about is just the difference between a variable and a constant. So I'm just going to start out with this with a little definition of both, okay? So a variable, what is it? A variable in mathematics is a symbol. Let's see, we're just going to start with, there we go. It's a symbol that represents, and sometimes you'll see as I write and talk, I'll misspell things, that represents a quantity, and since it's a variable, this quantity varies. So it represents a quantity that varies, okay? And this is typically, almost all variables are represented by a letter. So typically represented by a letter, okay? So this is when your famous X comes into play, right? When we do things like finding X, that's a variable that we're looking for, okay? The difference between that and a constant is that basically a constant does not vary. It is exactly what it sounds like, it's constant. So it can still be a symbol, so it's still a symbol, but this time it represents a quantity or a specific number that represents a specific number. Oops. See if I can spell specific right here, right? Fix that. Okay, so these are the things that aren't going to be represented by letters anymore. They are going to be represented by those numbers. So these are typically where we see that exact number that it represents. These are typically represented by numbers. But sometimes at first we will see constants represented by a letter, and then we'll realize that in context that letter is actually always just one single number. We're going to see an example of that coming up. So even though these are typically represented by numbers, these can sometimes they will be represented by a letter. And like I said, we'll see an example of that coming up. Sometimes represented by a letter. Whereas a variable cannot be represented by a number, because if it was a number, it wouldn't be varying. It would be that exact number. So these will always be represented by a letter. Where constant, sometimes you have to look closer into the context to see exactly what that symbol is representing. Okay, so let's look at some letters and determine what's going on with them. Okay, so we're going to look at some examples here of variables and constants and the difference between them. Okay, So you can kind of break that apart in your notes and make sure you realize here we're going to look at some examples. So our first example here that I want to look at that you can write down with me is that if S, there's our letter, our symbol representing either a constant or a variable, we're going to find out here in a second. If S is a car's speed in miles per hour, what is the meaning of S equal to 30? So S starts out as a variable here. It's just a car's speed in miles per hour. So we know that S could be several different numbers. It's varying. But what if we put a constant to that variable? We set it at 30. Then what does that mean? So if we set S at 30, then what we want to go back and remember is what S represents. S again is that car's speed in miles per hour. So now all we've done is set that speed to be 30. So this just means again that the speed of the car, and all of these things are going to seem redundant kind of, right? It already said that part in the question. We want to reiterate all of that because 30 is not just 30 miles per hour. What's going 30 miles per hour? The car is going 30 miles per hour. So very specifically, S equal to 30 is the speed of the car being, so what does it mean? It means the speed of the car is 30 and not just 30. Always put units with your numbers if they have them, 30 miles per hour. Okay, and MPH is just an abbreviation for miles per hour. And you want, again, all of that information there to explain what S equals to 30 means. Okay, so we're gonna do a little bit of a similar one here, but this one can be just slightly trickier. So I wanna look at this example. We're going to look at another symbol here. This time it's going to be the letter T. If T is the number of years since 2000, and we'll see variables set up like this a lot when we're talking about years. It'll be years since a certain year. So if T is the number of years since 2000, what is the meaning of T equal to 13? So think about that for a second. Now, if T is 13 and T is the number of years since 2000, what is the meaning of T equal to 13? So here now we're not just going back and kind of reiterating the question, we've got to do a little bit of math here. If we want the number of years since 2000 to be 13 years since 2000, then we need to take that starting year, add T to it, because that's the number of years since the starting year, to get 2013. So we're talking about the fact now that T equal to 13 means T is the year. Now that we've set it to be a constant, T is now the year 2013. And that's our final answer there. Okay, so T started off as a variable. We made it a constant by setting it at 13, and then we wanted to put that number back in context of the variable to really understand what that constant means. All right, so hopefully that helps you kind of understand what variables, how we typically set them up, and how important it is to always define a variable clearly. All right, we're going to look at one more example here where we have several different symbols going on, and we want to determine if, again, their variables are constants and what that means in the context. So in this case, we're going to look at a rectangle, or we're going to at least think about a rectangle. We're going to think about a rectangle that has an area A, so just capital A is a symbol that represents area, a length L, so L is representing the rectangle's length, Oh, and you know what? I need to put a little something else in here. Specifically, that length is going to be in inches. And that rectangle is going to have a width represented by a capital W. And that width is also going to be in inches. Okay, so we have three symbols corresponding to this rectangle. So far, we don't know anything else about those symbols other than what they represent. We're given more information though. We're also given that the area of the rectangle we're looking at, we know what it is. It is 12 inches squared. Okay, so this is all the information we're given. So with this information, can you classify whether A, L, and W as a variable or a constant? So determine whether each of those symbols are variables or constants. So let's just start with the first one in that list, A. Remember, A was the area. So can A vary for this rectangle? Can this rectangle be several different areas, or is that area set at one number, making it a constant? So as we're thinking about A, go back to your question. We know it has an area A, but area comes up again, right? We know that the area of the rectangle is 12 inches squared. That means that letter A can be nothing other than 12. It can't be 13, it can't be 200, it can't be any of those numbers because we know that this rectangle has to have an area of 12. So since A is set at 12, this means that A is a constant. It always has to be, for this particular rectangle, since we were told it had to be, always has to be 12. Okay, so now think about the fact, since we know that the area of the rectangle is 12, what do we know about L? And we can kind of think about L and W maybe together. Okay, are L and W set at something constant, or could they be different? Now you have to remember the only thing we know about this triangle is the area, right? We weren't told that the length was one specific thing, and we weren't told that the width was one specific thing. So we have to do a little bit of critical thinking here. And anytime I have to do some critical thinking, I always like to draw a picture if I can. So I'm going to draw a picture down here of a rectangle and think about the fact that how A, L, and W are related. So remember that the area of a rectangle is always length times width, which in this case we know is 12. So what I'm really thinking about here is, are there different numbers I can use for L and W to get a length of 12, or sorry, an area of 12? Or do L and W have to be very specific numbers and only one number to get to an area of 12? So what numbers can you think of? And it turns out that there's multiple numbers that L and W could be. L could be, right, we know 3 times 4 is 12, so L could be 3 and W could be 4. Or we could switch those around. It could be 4 times 3 and make L 4 and W 3. Or we could use 6 and 2, or 2 and 6 to get an area of 12. Or finally, we could use 12 and 1, or 1 and 12 to get an area of 12. Okay, so what you're seeing here is that the variable L could be 3 or 4. Oh, sorry, that's kind of making them look like negative numbers. It could be 3 or 4 or 6 or 2 or 12 or 1. It doesn't matter how many different things it can be. If it can be more than one thing, that automatically means that L is a variable. It's not set at just one number. So L is a variable. Because it can be more than one number, it's a variable. It is not set at one thing. And for the exact same reason, over here again, we see W can again be this entire list of numbers that means that W is not set at just one thing, so W is a variable. Okay, so that's the difference between a constant and a variable. If that letter can only represent one number, it's constant at that number. If it can be several different numbers or just basically more than one, then it's a variable. It can vary in its amount. Okay, so you'll have some questions like that coming up on your homework too. So hopefully that helps you kind of sort through the difference between a constant and a variable. Now, like I said, this section is kind of a mixed bag of things. So we're going to move on here to kind of a whole new topic. Okay, we're going to move on to graphing numbers on a number line. Next topic in this section. Graphing numbers on a number line. And it does kind of go with what we were just talking about, because this is a good way to represent several different numbers all at once. So let's connect those two for a second. Let's graph, if we're just going to graph some numbers on a number line, let's graph all those possible values that we had for L. So L could be 1, 2, 3, 4, 6, or 12. That's what we learned from the last problem. So if we want to graph all of those numbers on a number line, what's a good way to do that? So these are all whole numbers. We don't have any decimals or fractions going on. So I'm going to just create a number line. So remember, a number line is just a line where we put two arrows on either end. And we want to evenly space tick marks on our number line. So I'm going to work on that here. And as I'm thinking about how many tick marks I'm going to need, I need to go from 1 to 12 on this number line. And I'm just going to go by whole numbers. So I could think about this first tick mark as 1, then 2. So I'm going to need 12 tick marks here. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And anytime we're making a number line, it's okay. I could add more tick marks. We can have more tick marks on here than we need. Okay. And you can label each one, or you can kind of skip around, because if you know that's 3 and it goes to 5, right? I could maybe label a few less numbers here. 5, 7, 9, 11, 13, 15. Okay, or you can label every single one and put in 2, 4, 6, 8, 10, 12, 14 there as well. Just make sure you label enough so you can tell what all the tick marks are and what the pattern is there. Okay, so now I have my number line, but I need to specifically plot these numbers up here. So what I'm going to do is put a dot on the line for the numbers that I want to represent. So L could be 1, it could be 2, 3, 4, 6, or 12. And so now I can visualize all those different numbers that L can be. All right, so we've plotted numbers on a number line. Now, whole numbers tend to be the easiest thing to plot. So I also want to look at another example where we don't just plot whole numbers, where we've got some fractions going on in here too, because that tends to be the hardest thing to think about plotting. So now I want you to graph these 5 numbers. -1, so we're also going to think about negative numbers here. 2/3, there's a fraction. Throw another whole number in there. -9/5, so a fraction and negative. And another fraction to plot 5 halves. And getting a lot of different denominators of our fractions in there to see kind of what's going on here. Okay, if you have a calculator, it can be useful to think about your fractions as decimal numbers at first, just to kind of get an idea of how far spread out you're going to need your number line to be. So thinking about the fact that 2/3 is about 0.66, okay, or the fact that 2/3 isn't quite 3/3 yet, so it's going to be between 0 and 1. -9/5 is going to be between, it's a little bit over -5/5, right? So it'd be like -5/5, and then 2 would be 10/5. Okay, so -10/5 down here. So it's somewhere in between -1 and -2. Thinking about 5/2. So think about your halves. You have 2/2, then you have 4/2. That would be 1 and then 2. 3 would be 6/2. Okay, so that means 5/2 is somewhere in between 2 and 3. Or plugging in 5/2 into your calculator, you would see that that's 2.5 and fits right there in the middle. Okay, so basically our number line needs to span from as low as -2 to as high as +3, because we also have a 3 here. Okay, so you kind of have to think about those things first before you start setting up your number line. If you're already given a number line, then you don't have to worry about that particular part. Okay, but we needed to worry about that because we weren't given a number line from the start. So I'm going to set up my number line. Just to keep things simple, I'm going to go from -3 up to +3. And remember, your negative numbers increase, all the numbers increase from left to right. So -3 is smaller than -1. 0 is in the middle of your negative and positive numbers. And then you continue to increase as you go to the right. So that's how I'm going to set up my number line when I have negative numbers involved. All right, and then I'm just going to go down the line here. So we have -1 first. That's a nice easy one to plot. There it is, -1. And then we get to the first tough one, 2/3. Again, 2/3, always think in terms of just thirds. So we have 1/3, 2/3, 3/3. 3/3, 3 divided by 3 is 1. So here we have 0/3, and here we have 3/3. So somewhere in between those two is 2/3. Anytime you have a fraction, look to the denominator. That's how we need to break up the distance between 0 and 1. It needs to be broken up into 3 equal steps. That means you always need one less tick mark. I need 2 tick marks in between to get 1, 2, 3 equal sections. Okay, now I'm going to erase some of that so we can see what's going on here. So I've got 3 equal sections between 0 and 1. This first one would be 1/3, the next one would be 2/3. I'm going to try that again just real quick to see if I can get that to look a little bit more even. You know, we're doing this by hand, so it's not going to be exact, but that looks a little bit more even. So 2/3 would be sitting right here. Okay, and I'm going to write that one in just so I remember I've already graphed that one. And then I can kind of erase these notes to myself afterwards. Okay, the next one again is a little bit easier. At 3, we can mark that guy. Now, the next one gets a little harder again, -9/5. So immediately I know I need to start going to the left of 0 for -9/5 because it's a negative number. Think about your whole numbers again. -1 is -5/5, and -2 is -10/5 because 10 divided by 5 is 2. That means -9/5 is somewhere in between those. But now we need 5 equal spots, which means we need one less tick mark, 4 tick marks in between -1 and -2. So here we go, 1, 2, 3, 4. And again, I'm just going to do my best by hand to make those as equal as possible. Now, count those fifths. Remember at -1, we had -5/5. So as I move to the left, here I have -6/5, -7/5, -8/5, and finally right here, just before -10/5, I have -9/5. So again, I'm going to erase my notes here, but I am going to go ahead and write that in so I remember that I plotted that point, -9/5 right there. All right, see if you can try this last one. Maybe pause the video and then see if you do it right. So 5/2, that's positive, so we're looking to the right of 0. Think about your whole numbers in terms of that new denominator. So 1 is 2/2. 2 is 4 divided by 2, so we haven't quite gotten to 5 divided by 2. We need to keep going. 3 is 6 divided by 2. All right, so that means 5/2 is somewhere in between these two. I have 2 as a denominator. That means I need 2 equal sections between 2 and 3, which means I need 1 tick mark to divide it into 2 equal sections. This was 4 halves here at 2, which means if I go 1 more half, I'm right where I need to be at 5 halves. And then I can erase kind of my thought process here. Okay, so now we've plotted all 5 of those numbers, and that's a really good way to plot fractions. Okay, thinking of your whole numbers first in terms of that same denominator you're looking at, and then plotting in between those 2 numbers. All right, that is graphing numbers on a number line. The next thing we're going to get into is graphing inequalities. Now, if you need to take a break, we've done quite a few topics so far. Make sure you pause the video anytime you've kind of had enough there for a little bit and come back to it. Okay? So our next topic here is going to be graphing inequalities. So not just graphing numbers, but graphing inequalities. So before we get to graphing inequalities, I do just want to review really quick what an inequality is. So an inequality is all your symbols of less than, greater than, less than or equal to, and greater than or equal to. So here again, less than, greater than, and then when you see that line underneath, you've just got that same symbol. So this one's the one like the top, so it's still less than, but then if that line is underneath, it's or equal to. So we can be less than a number or equal to, and this last one is then greater than or equal to. And those are your 4 inequalities to remember. Okay, just a quick review of those. Coming into this class, we're kind of assuming that we've seen these before, but we did want to review them really quick. So we can again remember what these inequalities really mean and understand them by actually graphing them. So that's what we're going to do next. We're going to do some examples of graphing these inequalities. Okay, so let's look at some examples here. This is a really good way to visualize what those inequalities mean. So in these examples, we are going to graph each inequality. Okay. All right. First one I want to graph is x greater than 3. So there's a few things coming into play here that we've already talked about. X is my variable. That x is a variable because it can be any number greater than 3. So 4, 5, 4.5, 4.2, 100, right? There's a lot of different numbers. In fact, an infinite amount of numbers that this x variable can be. So I want to visualize that on a number line. So my very important number here is 3. I want to make sure 3 is on my number line and that I have numbers around it. Now, you can do this kind of in any way that you want. Just make sure, again, that 3 is on your number line and you have numbers around it. So if I have 3 right here, I could have 4, 5, 6, 2, 1. It could be centered always. You just kind of set up your number line so that you, again, make sure you have this number and numbers around it. Okay? Now, remember again, this symbol we're looking at is the greater than symbol. That means I want all these numbers greater than 3 and all the numbers in between too. So I want all these numbers greater than 3, anything in between the numbers too. So I shade all of those things and I put an arrow on the end of that shading to show that it goes on forever, that infinite number of things greater than 3. Oh, and my battery's getting low, so I might have to pause here in a second. Okay, now this is different than the greater than or equal to part, right? So x could not be 3. So what we don't want to do is fill in 3 showing that x could be 3 because it's not equal to. So what we're going to do instead is anytime we cannot be equal to that number, we can be really close to it though. We could be 3.1 or 3.01, right? We can be infinitely close to 3. So when we can't include that number, but that's our boundary point, we're going to put an open circle at that number to show we can get really close to it, but we can't actually be that number. okay? And right here, we've solved it. We have graphed that inequality x greater than 3. Okay, so let's look at an example with one of those less than signs, and let's also throw the equal to in. So now I'm going to use the variable y, and we're going to make that variable less than or equal to -2. So again, I want a number line set up over here that has -2 in it somewhere and numbers around it. So if I go to the right of -2, I get to -1 and 0. If I go to the left, I get to -3 and so on. Okay, now this time my symbol is less than or equal to -2. So this time I can be all the numbers less than -2. So this time I shade to the left of that number of interest, which is -2. And this time I have that equal to portion, right? I have that line right there. So I can be equal to -2. So instead of an open circle, I'm going to fill in that circle at -2 to show that y can also be -2 and still satisfy this inequality. So that's your difference between an open circle and a closed circle, a greater than and a less than sign. Okay? And this again would be our final answer here. I tend to like to box in my final answer. Sometimes I'll forget to do that though. All right, one last inequality we want to look at that's a little bit different is one that doesn't go on forever in one direction. So I could put a cap on either end here. I could say -1 is my smallest number my variable can be, and I can put an upper cap on that number too. And that always looks like this type of inequality, which is often called a compound inequality. So what this is saying is that m can be greater than or equal to -1, but less than 6. And notice how this one was a greater than or equal to, because m is on the bigger side of that inequality. M is greater than or equal to -1. We've just kind of reversed the way that inequality looks. So try not to get too confused by that. Okay, always pay attention to what side the variable is on. I kind of always remember it as the big side is the greater thing and the small side is a smaller thing. Some people draw fish and they're eating the bigger thing. There's all kinds of tricks out there for remembering how to remember the difference between a greater than and less than sign. Okay, so what this means though is that m is sandwiched between -1 and 6. So we need to make sure that both of those numbers are on our number line. Okay, so I'm going to start down here and maybe just past -1 to kind of remind myself what goes on around -1 and 6. So -1, then to 0, 1, 2, 3, 4, 5, and 6 is about all I can fit, and that's okay. All right, so think about this. M can be all those numbers between -1 and 6. So I need to shade this time, not forever in one direction, but just between that -1 and 6. And now I just have to think about, do I need closed or open circles? At -1, m can be -1 because I have that equals to sign. So you should have a closed circle here, but m cannot be 6. It has to be less than 6. But my boundary is right there at 6, so I'm going to put an open circle at 6. Okay, so there's my final answer right there. This is representing the values of m visually. Okay. All right, let's put one of these inequalities in context to kind of see when we would actually use an inequality for a variable. So in this example, I'm going to let W be my variable, and it's going to be the daily coffee consumption. I don't know about you guys, but I often need coffee to get through the day. The daily coffee consumption, we always need a unit for a variable. So this is going to be coffee consumption in ounces of a person. So this is a variable because it can be a bunch of different things. But what if we put an inequality to this variable? I want you to graph and interpret what W greater than 8 would mean in this particular scenario. So let's graph that first. How would you graph W greater than 8? Your point of interest, your main number there is 8, so make sure 8 is on your number line somewhere. You can go up to 9, down to 7, 6, 5, 4. You can do it in any way you want. You can put 10 on here too. Okay, you could have put 8 towards the bottom. You can do whatever you want when you set these up, just as long as you have that number with numbers around it. And then graph W greater than 8. So when you graph that, did you put everything here greater than 8, shade it all with an arrow at the end? And then did you make sure you had an open circle at 8 because W cannot be 8? There is no equal sign underneath that inequality. So that is the graph of W greater than 8. But what does it mean for W to be greater than 8 in this particular case? So remember what W means. It's the daily coffee consumption of a person. So just put that in place of W. It means that the daily coffee consumption of a person is greater than 8, is more than 8, what? 8 ounces of coffee. So you can say that kind of in a bunch of different ways. I'm going to just kind of summarize it down here. So to me, that means that this person, whoever we're talking about, right? We're talking about a person too, not some animal or something else, right? Like that, right? A person in particular is consuming this coffee. So this person drinks more than, right? Not less than, but more than 8 ounces of coffee. And don't just stop there, right? Because it was daily consumption. So they drink more than 8 ounces of coffee a day, not just in general, not a month, right? We know they drink more than 8 ounces of coffee a day. So again here, very important, just like when we were working with variables before, not leave any part of that out. We got the coffee consumption part, right? We got coffee down there. We got the daily amount. We got the ounces. We got the person. Okay, we got all of those different things. We got the 8 in there, and we got the fact that it's greater than by putting more than. Okay, we needed to represent all of those different things. All right, so that's what that means in context and what it visually looks like on a number line. One last thing we want to talk about with inequalities is interval notation. So interval notation is another notation we'll use with inequalities. So I want to review that with you, and then you're going to have questions about it to also review in your homework. Okay, so all I'm going to do here, and your book is another good place. Make sure you're reading those sections before taking these notes. I'm just going to review some examples of interval notation. So far, like I said, this is related to inequalities. So far we've seen inequalities, and we've seen graphs of those inequalities. And now we're going to relate those things to what that looks like in interval notation. Okay, so it's just, again, another notation to represent an inequality. The graph is just a helpful middle step to help you get to interval notation, I think. Okay, so let's look at an inequality. Let's make a variable greater than 3. Making a very quick graph of that, I'm just going to put 3 on this graph right now because, again, I'm just doing this for to help me get to interval notation. 3, it's a greater than, so I need to go to the right, and it needs to be an open circle on 3. So my graph, my very quick graph of that looks like this. And now interval notation, I can create from looking at that graph from left to right. So interval notation, if you see an open circle, that's the first thing I see from left to right, then I've got a parenthesis for interval notation. Then parenthesis is at 3, so I put a 3, or sorry, the open circle is with 3, so I put a 3 with that parenthesis. And then the graph, as I read it from left to right, as it goes to the right, it goes on forever. Forever to the right is a very big positive number. That's what we call infinity, and that's the symbol for infinity. And infinity again gets a parenthesis because it's not a number we can be. Now, interval notation isn't always made up of parentheses. It can also be made up of brackets. And you'll see a bracket when you can be a number. So let's put an equals to sign underneath that inequality. When I graph it, that inequality notation is going to change, or sorry, interval notation is going to change as the graph changes. So again, I have it here at 3, but remember this time, I'm going to put a closed circle at 3 because I'm greater than or equal to 3 for this inequality. That means I put a bracket. A bracket means I can be 3. I put a bracket with 3 and it goes on to infinity in the positive direction. Okay? All right, there's going to be a little break in this video because I need to charge my iPad real quick. So I'm going to pause this for a second and then we'll come back, okay? Okay, that was a quick pause for you guys, a little bit longer of a pause for me. Okay, we just want to finish up going over this in interval notation. Okay, so here we go. Let's try some of those less than. So let's do x less than 3. So again, my quick graph here is going to include 3. And this time, since I'm less, I'm shading to the left. And I have an open circle again at 3 because I do not have an equals to inequality. As I look at this from left to right now, my first thing I see is that it goes on forever to the left. If I have my numbers as big as they can be to the left, that is called negative infinity. It's a very big negative number. Again, it's infinity, so it gets a parenthesis. I can go as far right then as 3, but not included, so it's a parenthesis. So that's interval notation representing that the variable x can be anything less than 3. All right, so try for yourself. What would be the interval notation for x less than or equal to 3? Your graph should look like this. It should have that 3. We're going to close the circle this time at 3 and shade to the left because it can be anything less than 3. So what changes is not the first part, right? We're still going to the left forever, but what changes is that we can be 3 now. So we include that 3 by putting a bracket in our interval notation. I want to look at some of those compound inequalities as well. Okay, with compound inequalities, you won't have infinities because you have 2 endpoints to your inequality. So here's an example. What if I have 2 is less than x and x is less than or equal to 5? Okay, so now I have 2 numbers that need to go on my quick number line, 2 and 5, and 2 is less than 5, so it'll come first. My variable can be anything in between these 2. Let me make sure I change that color real quick. There we go. And x cannot be 2. That's where I have my open circle. X can be 5 because I have the equals to part of the inequality there. So I've graphed it. But I need to make sure I get my interval notation correct. So from left to right, the first thing I see is an open circle because x cannot be 2. So I have a parenthesis for that open circle at 2, and then I have a 5, which has a closed circle, so it gets a bracket. So that's what compound inequalities are going to look like. So let's just do one more example of a compound inequality, and you guys try this one. So what if I had 2 less than or equal to x and less than or equal to 5? What if they were both included? What do you think that's going to look like? Again, a graph might help you here. Or you might be catching on. You might be able to go straight to that interval notation, which is great. If not, I still a lot of the time have to do these graphs just to visualize what's going on to get to that interval notation. So hopefully your graph had 2 closed circles since x can be both 2 and 5. So did you get the right interval notation? The first thing we can be is 2 up to the number 5, and that's our final interval notation. Okay, so again, just good review of interval notation, just another way to represent inequalities, something you'll see a lot in other math classes that kind of shortened representation of inequalities. I just wanted to make sure we understand how to get from one to the other. There'll be some good practice of that in your homework in my math lab. All right, very last topic. 1.1 is kind of a long one, but very last topic for 1.1 is just a review of plotting points. Okay, so if you remember how coordinate points look, coordinate points are always your X and Y. So what's a little confusing is seeing that right after interval notation. This has nothing to do with interval notation. This is just plotting points where we always have the X coordinate first and then the Y coordinate. And we always plot these on our Cartesian coordinate system, our grid here, where the up and down axis is always your Y axis and the left and right axis is always your X axis. So we just want to do a few examples here. On this axis up here, I want to review how to plot some points. So we are going to plot the point 5, 1, negative 4, 2, 3, negative 1, 0, negative 4, and 1, 0. We are going to plot all 5 of those points. So the highest number I see here is 5, so I'm just going to put 5 tick marks on each one of my axes out from that origin. So right here in the middle would be the point 0, 0. I haven't gone anywhere to the left or to the right. So I'm going to go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Just to set up a grid for myself. Now, if you're already given a grid, you don't have to worry about that part. You just have to worry about what each represent. So make sure anytime you draw a grid, just like with a number line, you label some numbers here so that your reader knows how much each tick mark is worth. So I went from 1 to 5 here, and my Y direction I went from 1 to 5. Now as I go to the left, I'm going from negative 1 to negative 5, because again, that middle point is 0. And as I go down, I'm going from negative 1 to negative 5. Okay, which is a little hard there. You can kind of see I'm trying to fit all those numbers in, but just do the best you can when you're drawing this by hand. But make sure you label it if you're drawing it by hand. Otherwise, the reader doesn't know what amount each step counts for, right? Because you could go by 2s or 5s or something like that. All right, but once we have that set up, we just want to plot these points. So how do I plot the point 5, 1? This means X is 5 and Y is 1. Always X and then Y. It's in alphabetical order, so that also helps us remember. So to have 5 in the X direction means I need to go 5 tick marks to the right. And to have 1 in the Y direction means I need to go 1 tick mark up. So right there, I have the point at 5, 1. Negative 4, 2. X and then Y. That means I need to go negative 4 in the X direction. To go negative 4 in the X direction, you go left 4, and then 2 in the Y direction means up 2. So go left 4 and up 2, and you should end up here where the green point is. All right, 3, negative 1. Give it a shot. Again, label X and Y if that's helpful. To get to this point, you should go right 3, positive 3 in the X direction, and down 1, because it is negative 5. Sorry, I don't know where 5 came from. Negative 1 in the Y direction. Now the zeros can sometimes get a little bit tricky. So I wanted to make sure I had zeros in both an X spot and a Y spot here. So on this one here, X and Y, X being 0 means you just stay here at the origin, you don't go left or right. But Y being negative 4 means you stay at the origin and you go down 4. So this point is going to be on that Y axis. Now our last point has an X value but a 0 for the Y value. That means from the origin, I just go in the X direction, 1 to the right, but I don't go up or down because Y is 0. So I just have this point here on the x-axis where x is 1 and y is 0. And that's how we plot points when we have two variables. We have that Cartesian coordinate system and we can plot both variables together. And we'll use that a lot to see how two variables are related here later in the class. All right. So that's everything you need for section 1.1. Hopefully that was helpful for you guys and that you're liking these videos. Again, that's a long video. So when they're long, don't feel afraid to pause in the middle, stop and go get some caffeine or something like that, right? Just take a brain break from it for a little bit. That's the awesome part about these recorded lectures is you can stop and start them and take in as much as you can at a time. Just don't forget to come back and watch the whole thing because everything in these videos is important for learning how to do anything in this class and helping you do that homework and helping you get ready for those quizzes and tests, okay? So again, reach out to me anytime you have questions and I'll post these videos with each section. All right, have a good one, guys.